Hello, my name is Andrew Hardy, and I'm going to be presenting on a multiflavour SYK model on a lattice. Now, this is work that I've done with my supervisor, Arun Permakanti, and one of his postdocs, Arjit Halder, here at the University of Toronto. Thank you for listening. So to start with, I'm going to look at some real material motivation for the model that we've constructed. So what I have here is iron selenide, thin film strontium ruthenate, and magic angle twisted bilayer graphene. Now, what do all of these materials have in common? There's some common themes that we can extract here. The first of which is that they're all strongly correlated. Strontium ruthenate, for example, is a confirmed non-Fermi liquid, or flat bands in bilayer graphene amplify interactions. And also, all of these systems have a so-called nematic phase transition, where there's spontaneous breaking of discrete crystalline symmetry, either 90 degrees C4 or C3 symmetry. And so this so-called nematic that you see in the phase diagrams on the right is this breaking of the symmetry. And lastly, they all have multiple degrees of freedom, such as multiple valleys, and they have a preferred direction with anisotropic hopping. So such as in a 2D plane, the dxz and dyz orbitals have a preferred direction. So with this motivation, we can ask our motivating question, can we construct a solvable model that transitions from a non-Fermi liquid to nematic order? Now, how are we going to go about doing this? So we start with the canonical solved model for a non-Fermi liquid, which is the SYK model, which I'm sure you guys have heard a lot about already during this session in March meeting, but just to review, it's a all-to-all coupling of 4 fermions with some random coupling constant J that has some probability distribution with 0 mean and a variance of some constant J squared. So what you have here is 2 orbitals given in blue or red that both contain this SYK type interaction labeled S and S prime. And these 2 orbitals also interact via an SYK type interaction, this VSS prime here, given in the green arrow. And similar probability distribution. And lastly, we place these 2 orbitals on a lattice. So this is a square lattice hopping, but you notice that there's some anisotropy put in here where each orbital has a preferred direction. So the s orbital here in red prefers the x direction, or the blue orbital here prefers the y direction. So s prime has greater hopping in the y direction and less hopping in the x direction. So you can see here we have this nematic schematic that displays C4 symmetry cross some Z2 switching of the orbitals that I rotate 90 degrees and change my labels, and I have a symmetry here. And now we can look at the phase diagram for this model. So one of the advantages I mentioned of the SYK model is that it's exactly solvable, that through a large n limit and by disorder averaging, we can find a saddle point solution that is exact, and we are able to get Dyson equations that then through this DMFT type algorithm, we can get self-consistent solutions for both the self-energy here and the Green's function here. So what I have is per orbital labeled S, sigma and G. So you can see here sigma, the first term is the self-energy that is typically present for an SYK model, plus another SYK type self-energy switching between the flavors, weighted by the population ratio, this eta of the 2 flavors. And then the Green's function just has an increased epsilon k dispersion. So when we solve these self-consistent equations, we're able to find the free energy, and we can look at thermodynamic properties. So what I have here is a phase diagram of polarization. So this is changes in population between the 2 flavors or orbitals, so that there's some favored flavor that builds up a population. And you see here for low hopping, this is a first order transition that it immediately saturates the polarization, whereas for the above 0.1, there's a second order transition here. And you can confirm this by specific heat calculations, but the above 0.1, this is now a smooth continuous growing in the polarization as compared to just the first order. And again, in this first order, we notice that the compressibility here given by kappa goes to 0. So this is inverted colors, that at low temperatures, the first order phase is completely incompressible, whereas the second order phase remains compressible. So this is a common theme that you'll see here, is that this gives an intuition that the first order phase is going to be an insulator, whereas the second order phase is going to be metallic, and that we can draw parallels between transport properties and thermodynamic properties. So before we go on to that, let's conclude with a full 3D phase diagram. So you have here in the X direction delta T, and in the Y direction T for hopping. So delta T is the amount of anisotropy. And again, we see in navy, there's a first order transition, and in gold, there's a second order transition. And so there's this line of tricritical points that distinguishes between the two of them. And this line of tricritical points is decreasing in temperature. The critical temperature is decreasing as a function of increasing anisotropy. So we have these three distinct regimes, and now we want to extract transport properties about the three regimes. So what I have here are three spectral functions. So in order to find transport properties through the Kubo formula, I want the spectral functions here in real-time frequency. So numerically, a Wick rotation is too difficult. So we do self-consistent equations again in real time. And here we have the imaginary part of the Green's function as the spectral function. And we can find three distinct regions of spectral functions that correspond to the three regions of our phase diagram. So to the left here, you see that after breaking particle hole symmetry, the polarization breaking slowly decreases the spectral weight at omega equals 0, as these square lattice density of states gives a sharp V shape. However, in the nematic metal region, we see that there is the same symmetry breaking, but it's much subtler, and so the spectral weight remains. And then when the symmetry breaking is suppressed, particle hole symmetry is retained for both flavors. So now with this, we're able to do through a Kubo formula, which another advantage of the SYK model is this is exact in bubble order. We're able to extract the conductivity and then the resistivity. And now we have this order parameter n of the differences between rho x minus rho y. And you can see here in the lower left, there's this insulating dome that corresponds to this nematic insulator, whereas there's a swath of a nematic metal that continues down to low temperatures, dubbed here by the nematic metal. And then when symmetry breaking is suppressed, we have this isotropic metal. So again, we see this phase diagram that roughly corresponds also to our thermodynamic calculations. And so I'm going to look at some cuts here in the resistivity. So some common themes here is that at high temperatures, you have a T linear scaling of the resistivity, which, as a lot of people have been pointing out, is a sign of these non-Fermi liquids and a lot of exotic properties that deal with this linear resistivity scaling. But then after undergoing this symmetry breaking, we have three distinct regimes that we can point out. So on the left here in the insulating regime, you have this asymptotic growth of the resistivity as it becomes insulating. However, in the nematic metal, you have this transition to a Fermi liquid, some kind of quadratic power law scaling here. And then lastly, for when spontaneous symmetry is suppressed, you just have retained this T linear scaling here. So again, we're able to extract these properties through transport. And so lastly, in conclusion, I have a nematic phase diagram here. So this is at low temperature. So now the y-axis is this anisotropy delta T. And you can see here that the scales are slightly different, but the polarization thermodynamic plot and the nematic order are equivalent, that there's this left regime that shows strong polarization for first order transition, and also shows a nematic insulator. However, there's this triangle of a nematic metal that's partially polarized and retains a metallic nature. And then again, there's lastly this suppressed region. So with that, we can conclude with our main points that lattice SYK models can serve as solvable models of nematic order with strong interactions, and also that this model illustrates non-trivial criticality, that there's this line of tricritical points, thermal tricritical points that divide the nematic metal to the nematic insulator transition, and that they're decreasing in temperature. So lastly, I'd like to thank my collaborators, again, my supervisor Arun and Arjit, who have been very helpful, and my graduate funding from NSERC and CFAR for helping me to come here. So thank you guys so much.